Welcome back. We are talking about forces, and we're going to divide them up slightly differently. So, forces. Now, there are two types, conservative and non-conservative. Now, you might be thinking, what about F-town? Aren't there other types than just conservative and non-conservative? Well, each of those forces gets broken up into one of those two categories. But for right now, let's just talk about a different way of looking at the forces, conservative and non-conservative. So we have F sub C, F sub NC. It's not conservative liberal, it's conservative non-conservative. So as we're looking at F down, and the big question that I'm sure all of you are asking is, what about F down? Only one is conservative, and the question is which one? Now this is the easy part right here. Now it does require a little bit of memorization at this point. That there is a formal definition for conservative force, but that's beyond the scope of 110, so I'm not going to worry about it. So if you want something more, just ask and I'll be glad to tell you. So the list of conservative forces, I'm going to list out all the conservative forces that you could possibly use for this course, or 151, 152, 251, 252, all the physics courses offered at Forsyth Tech. Here's the list. Gravitational force and weight. At this point, that's the only one that you will need. Eventually, we'll add in elastic spring forces. The word right above elastic is the word ideal. And then, of course, I just exposed it, the electric force, that is the last one. So those are it. We have gravitational forces, we have elastic or spring forces, and we have the electric force, which we get to near the end of the course in 110. So, great. Let's call it conservative or non-conservative. Is there something that's actually conserved? So, what is conserved or not? Well, this is the big question right here. Why do they call it conserved? Well, this brings in energy. Energy is what is conserved or not conserved by these forces. Now, if you recall, or go back to your readings, we have energy symbolized by the letter E. There are three types of energy. We have kinetic, symbolized by the letter K. We have potential, symbolized by the letter U. Why? Why U? I have no idea. But U. More advanced textbooks, especially in electricity and magnetism, like to use the letter V, but we use V in this particular course for electric potential, so we're sticking with U. Some people like to write out the word potential energy. That's too much writing for a physicist, so we just use the letter U. And then the last one I throw in there just for completeness is rest energy. And as it's written there, it's ignored mostly in Physics 110. Rest energy really doesn't matter in classical physics. It only shows up, only has any bearing whatsoever when you are dealing with, when you get into relativity and relativistic mass, the fact that the mass changes as an object gets faster. Now, if we ignore rest energy, then what kind of energy are we talking about? Well, that's mechanical energy. So if we're looking at the total energy would be the kinetic plus potential plus the rest energy, but since we're generally ignoring that, we have generally what is now called mechanical energy. Just kinetic plus potential is equal mechanical. These are scalars, you just add them straight up. If I've got 5 joules of kinetic and 3 joules of potential, my total mechanical energy is 8 joules. Now, you'll find that textbooks often will drop the word mechanical and just say the energy. Well, yeah, that's just the way that we do it, which you're just supposed to know. Now, why do I care about conservative, non-conservative forces and energy? Is there some connection? Why do I care? Well, because of the work-energy relationships. That's why. And that's the whole point of this particular video, is to talk about that. So let's first recall that work is force times displacement. And so it's going to get really tricky here. Conservative work is conservative force times displacement. And non-conservative work, oh, I'm sure you can guess it if you haven't done it already, is non-conservative force times displacement. Clever the way they come up with this terminology. Now, since conservative, and this is not an official proof right here, this is sort of the memory trick, conservative forces conserve energy. Non-conservative forces don't conserve energy. So, the first work-energy relationship that I'm going to reveal here is the fact that non-conservative work equals the change in energy. Whatever the total non-conservative work is, that's your total change in energy. The net work, the total work is equal to the change in kinetic energy. That should not be a shock if you saw the PowerPoint presentation where I sort of go through the math on that one, or if you didn't understand the math, then I guess perhaps that is a surprise. But there is actually mathematical derivation of this. The non-calculus version is posted. There is a calculus version which comes out to the same answer. Now, since total work is conservative work plus non-conservative work, we can then take this idea that the total work is conservative plus non-conservative, which is the change in kinetic. So I'm just bringing down this value right here. And then we have this change in energy minus potential energy, because if you recall, energy is kinetic plus potential. So kinetic is energy, total energy minus potential. And so therefore we have this change in energy minus the change in potential. Well, since non-conservative work is equal to the energy, they are equal to each other. See if I can split my fingers right there. And therefore they would cancel out, and what I'm left with is the conservative work is the negative change in potential energy. Now you're going, wow, that just blows my mind. But how do I actually use this? Well, it actually shows up in some of the other videos and some of the derivations that we do elsewhere. But just the big thing is this whole work-energy relationship is something to which I will make reference, and so you should understand the terminology. Recapping the work-energy relationships, we have non-conservative work is equal to the change in energy, the total work is equal to the change in kinetic energy, and the conservative work is equal to the negative change in potential energy. And there you go. No matter what level of physics you're doing, those three relationships are true. Why? Because work and energy are defined to make it true. There it is. Rejoice.